So I realized that I should probably explain what a limit is before doing anything else related to calculus because, well, in my opinion, limits are the calculus technique. So limits are always expressed with this, like, we're gonna say a for f of x. Whoops, I should redraw that bracket. So limits are always drawn with this type of notation where it's lim as x with an arrows, meaning that x approaches this value a. A is our substitute for any real number, honestly I feel like it could be any impossible number as well, just any number. Um, yes, it can be any number, or any quantity, because that will get explained later. And then you write, usually either in brackets or not brackets, you can just write it like, what the hell? You can just write it like this, x approaches a or f of x. I always like using brackets, it helps me look at things better. And for this case, let's say that f of x is equal to a simple x plus 4. So let's say that a is 5. So we're going to write out the limit of x approaches a of, you can either write in f of x or just write in x plus 4 directly, and it will equal, well, the value of f of x as x approaches a is 5, and in cases like these we can just plug in a into x. So we're just going to say 5 plus 4, which equals 9. Makes sense. When you're also given a quantity for what a equals, we can also just write limit as x approaches 5. Whoops. X approaches 5 for f of x. And that is well for using it to solve problems, so what is actually a limit? And for that, I'm going to have to draw a graph, which I don't like, but you just have to, I guess. So now that we have all of this out of the way, we're going to draw simple graph 1, 2, 3, 1, 2, 4. And then we're going to say we have this graph. And obviously we know what this graph is, or what I'm trying to do here, with this being the origin. Obviously this is the function of that, yes. And this is supposed to be 2, 1, 4, 2. So let's say we're trying to figure out what this point is, right? We would, what a limit is, so this is 3. So what the limit actually looks at is what value the function is approaching as it comes in from the left side and from the right side. And that's why we just write it as this. So that makes it look like a matrice. But with a simple function like this, it will just be plugging in 3 into the equation like how we did with 5 earlier. So it equals 3 halves. Makes sense. But let's say our, thing was a little bit more complicated. Or I can show what makes this another way to write this that will be important later as we go into more complex versions. So you can look at what value the function approaches from either side by putting either a negative or a positive symbol in like where you would put exponents to the number. So here, this only looks at function f of x. This only looks at f of x as x approaches 3 from the left side. It's still 3 over 2, but you can maybe start getting inklings of why this is important. And obviously, if we were to do a positive symbol, it would be only looking at the function as x approaches 3 from the right side. So now we have this, which is the same thing as saying, well, when we have the right side and the left side equaling the same thing, that means that just the general x approaches 3 is a valid number. So you might ask, well, when does this not apply in this way? Limits become the most important, or reach very important levels when looking at functions that have breaks or jumps. That's what we call them. Or, like, for example, like rational functions. I don't actually remember much about rational functions, so bear with me. But if we just have, I'm just gonna draw it out. I don't know what this is. We're just gonna, we have to make this actually a function. Boom. But we're gonna say that there is a, where's your point? We're gonna put it at x equals 2 specifically to make it simpler for my articulation. And we gotta put that at 1. So we have this function. If I were to say, what is f of 2? The actual answer would be f of 1. Or, what? No. The actual answer will be 1. However, if, let's say this is like 2.3. If I were to say, what's the limit as x approaches to for function f of x, the answer would actually be 2.3 because both on the left side and the right side, the value approaches 2.3. This can also be done for functions that have holes in them, which is why I tried to bring up rational functions earlier. Here, the limit will still be 2.3 because both the left and right side go to that point. However, the actual value of f of 2 will be undefined, which we write with und. I write in cursive, so it's und. Now, here's the part where sided limits become very important. So we're going to still call this a graph of f of x. We're just going to remove this part where it says 2.3. And we're going to this is like something about, actually, I should probably make this up the color so it's simpler to see. So we're gonna make it this dark red. I just like this red. So we're gonna make it here, and then at f of 2, we're gonna say. So we have this. This is surprisingly a graph you see a good amount in calculus, but this is graph f of x. If I were to take a limit as x approaches 2 for f of x, you would not, you'd realize, okay, well, from the left side it's 1, from the right side it's 2. Though 1 isn't 2, to say it bluntly. And that means that the limit as for f of x, or the limit as x approaches 2 for f of x is, nope, we right, does not exist, represented by big D and E. However, we can still take sided limits. So if I were to look at the left side of the function, or left side as of 2, so we're going to write limit as x approaches 2 from the left of f of x, that equals 1. And the limit for x approaches 2 from the right for function f of x equals 2. And we're going to write since limit of 2 minus f of x, and I'm going to use a bit of like programming notation, does not equal boom, does not equal f of x as x approaches 2 from the right. The actual limit for x approaches 2 for function f of x does not exist. Actually, realistically, since I'm writing this out, I don't have to use programming notation. I can just boom. How great is that? I think that's all for limits, actually. Wow, this is surprisingly quick when you already know it.